There's another law called Avogadros Principle, and this is where we first get to start to play around with numbers of moles. Avogadros Principle says equal volumes of gases contain equal numbers of moles. And that's true for any gas, but here's the restriction. The temperature and the pressure have to remain constant. An important consequence of this is something that we call standard molar volume. 1 mole of any gas, it doesn't matter what gas it is, will take up 22.4 liters at this set of conditions that we call standard temperature and pressure. Standard temperature and pressure is abbreviated STP, and the standard temperature is 273 kelvins, and the standard pressure is 1 atmosphere. Well, you can use this fact to solve some problems that allow you to convert from moles to volume or volume to moles, as long as you happen to be at STP. Like this problem. It asks how many moles of gas are in a 2.50 liter container if it's at STP. Well, if I have 2.50 liters of gas at STP, and I know that 22.4 liters is the space occupied by 1 mole at STP, well, liters now drop out, and I'm left with moles. Then I just do my arithmetic. I'll have 3 sig figs in my answer. 0.112 moles is how much gas is in that container. Well, there's one more law that would be nice to have, and that's one that allows us to change all 4 of the variables: temperature, pressure, volume, and number of moles, and solve for an unknown. Let's develop it by looking at the relationships we know that involve volume. We know from Charles's law that volume is equal to a constant number times temperature. It's directly proportional to temperature. We know from Avogadros' principle that volume is directly proportional to number of moles, which we're going to call N. We know from Boyle's law that volume is inversely proportional to pressure. So taking these 3 relationships and putting them into one law, we could say volume is equal to a constant number of proportionality times temperature times number of moles, but divided by pressure. Now, the constant of proportionality here turns out to be an extremely important number, and it has a value outside of even the study of gases. You're going to see this number show up at many, many instances. We give it a special name. It's R, capital R, and this is called the universal gas constant. So let's put that in instead of K. Volume is equal to R times T times N divided by P. This law is usually written a different way. Most of the time this is expressed as PV equals nRT. So that's called the ideal gas law, and it's a very powerful law. You can only use it, however, if you know what R is. So let's figure out what R is. If we take this equation and solve for R by dividing both sides by N times T, you get PV divided by N times T. Let's evaluate it at one condition, and it should be useful at all conditions because this is a universal kind of a law. The pressure we're going to use is standard pressure, which is 1.00 atmospheres. The volume we're going to use, well, let's pick 22.4 liters. Why 22.4 liters? Because remember, that's standard molar volume. That's the volume associated with 1 mole. So for N, we're going to put 1 mole. And the temperature we're going to use is standard temperature, which is 273 kelvins. So when the standard temperature and pressure are met, the number of moles is 1, the volume will be 22.4 liters. We know that these conditions all match each other, and so this will be a way we can evaluate for R. The unit is a complicated unit. It's liter atmospheres per mole Kelvin. Nothing drops out, so you got this complex unit. The value is 0.0821 to 3 significant figures. That value of universal gas constant, combined together with the ideal gas law, is a very powerful problem-solving tool. Like you could use it to solve this problem. How many moles of gas are in a 250 milliliter bulb at 740 torrs and 25 degrees C? Well, since we have information about moles, this is kind of my guiding principle. If I see information about moles, or if I'm asked about moles or mass of a gas, I have to use the ideal gas law. Otherwise, I can use one of the other laws. So the ideal gas law is PV equals nRT. And the question is how many moles, so it's N that I want. I'll solve my equation for N by dividing both sides by R times T. So N is PV divided by R times T. Now we're going to see a restriction here. R is 0.0821 liter atmospheres per mole Kelvin. Here's what that means. Temperatures all have to be in kelvins. Well, they usually do in the gas laws, so that's not a big issue. So when I put T in here, instead of 25 degrees C, I have to use 298 kelvins. Pressure is in atmospheres in the constant R units. So I can't put 740 torr in for pressure. I have to put in 740 torr in atmospheres. Here's how I can convert. 740 torr could be converted using this fact. 1 atmosphere is 760 millimeters of mercury, or 760 torrs. So this factor will allow me to calculate what is my pressure in atmospheres. And it's 0.973 atmospheres. So that's what I'm putting in here for P. 0.973 atmospheres. Volume. Well, my volume is 250 milliliters, but because the unit of volume in R is liters, I can't put that in here. My volume has to be in liters. So I'll convert. 250 milliliters. There are 1,000 milliliters per liter. Milliliters will drop out, and this leaves me with 0.25 liters. So that's what I'll put in for volume. Watch what happens to the units. Liters, gone. Atmospheres, gone. Kelvins, gone. The unit that's left is 1 over the reciprocal of moles. So, of course, that's just moles. Two significant figures in my answer. It's 0.0099 moles. So, to apply the ideal gas law, you have to use liters for volume, atmospheres for pressure, kelvins for temperature.